Okay, well, welcome everyone. It's a pleasure for me to welcome Ion Errea, our speaker today. Ion did his PhD at the University of the Basque Country, and in 2011 he finished and he went for a postdoc to the Pierre and Marie Curie University in Paris, and then back to San Sebastian and the Donostia International Physics Center. Since 2015, he's at the university as an associate professor, and since 2018, he leads the group on quantum theory of materials in the Centro for Materials Physics, and more things. In 2015, he was shortlisted as the Volkerheim investigator for the Volkerheim Investigator Award, and was selected emerging leader by the Journal of Physics Condensed Matter. Well, his research focuses on the development of theoretical methods to study complex the properties of complex materials, of complex solids, like electron phonon and things like that. And he applies all these methods to different materials like superconductors or thermoelectrics and many others. He has an ERC funded starting grant on the discovery and characterization of hydrogen-based high-temperature superconductors. And finally, let me stress that he's also very involved with other things beyond research or directly related to research. And he's now a corresponding member of Jakunde, who is a Basque Forum for Reflection on the Contemporary Challenges of Society since 2019. Okay, so, it's a pleasure to have you today, and he will tell us about superconductivity at ambient conditions, dream or reality. This is a topic that was a trending topic last year in the social media, which is not very common for the work we do. So we are all looking forward to your talk. Thank you so much.
Yeah, thank you very much for the invitation and this very nice presentation. So it's really a pleasure to be here with you. And yes, so I think I've been working on superconductivity mostly from an ab initio perspective. So I'm a theoretical guy. I'm doing ab initio calculations mostly. And yeah, last year it was like a boom, 2023 of the field of superconductivity. We had many news in the media. We were really, it was a big hype. So yeah, actually, so as you heard now, so my main line of research is the characterization and discovery of new hydrogen-based high-TC superconductors. So basically, we have been working on that. So yeah, there was like a bit of revolution, at least socially, in this field, right? So I want to give you like a broad perspective of what happened last year and what are the expectations, in my opinion, of the future of the field of superconductivity, whether it's just, smoke in the air, or there is something that, that can be well rooted, and we can have hopes of finding ambient condition superconductivity in the near future. So indeed, superconductivity is one of the most complex and interesting properties that happen in material science, right? So yeah, I always like to talk from the very bottom, right? So what is a condensed matter object? It's just nothing but electrons and ions that interact via Coulomb interaction. That's all. We know the theory of everything in condensed matter physics. We know our Hamiltonian. We know everything. But then, even if this simplicity, and we know the theory of everything, we have properties that we cannot understand. So this complexity of adding electrons and ions gives rise to very complex properties, very unusual properties, and superconductivity is one of those, right? So, superconductivity gives us a material that below a critical temperature loses all its resistivity and becomes a perfect diamagnet. So it's something kind of unbelievable, right? So the story of superconductivity began in Leiden. And I heard once that it came as a consequence of a big tragedy. So we are in Leiden, and this is year 1807, in the Napoleonic Wars. So there was a big boat, in the canal in Leiden, in the Netherlands, and it was full of gunpowder. And there was a big explosion. So it was a huge explosion. So 200 buildings were destroyed. 150 people pretty much died. So it was a big tragedy. So in these fields that were destroyed by the explosion, later, the University of Leiden built some new buildings, and in one of them, this laboratory. Okay, so this is the laboratory of Kamerlingh Ons, this man, right? So, yeah, very classical picture of the other times. Who was was a researcher that was capable of liquefying helium, right? So therefore, he could go to very, very, very low temperatures. So he could go around 4 Kelvin temperatures. So at that moment, they were trying to understand what was happening to the resistivity of metals when you were cooling them down to really 0 temperature. And there were different theories. They didn't know what was going to happen. But what they did not expect at all is that in mercury, what they were going to measure, this is the original picture of that they measured there in Leiden, it's that the resistance was going to disappear, right? Below, in that case, below 4.2 Kelvin, the resistance completely disappears. So I think they repeated the experiment like many, many, many times. They said, this is not physical, there has to be a shortcut, something going on. So they repeated it, and again, they had this result. So they published it, and yeah, that was the discovery of superconductivity. This is great, right? Because if we go to, I teach physics in the engineering school in the first year, so I put these formulas, right? We know Ohm's law, so this means that if the resistance is actually 0, we can have huge intensities, okay? You know that in a superconductor, we cannot have an infinite intensity, right? Because there is a critical current that actually from above this critical current, superconductivity is lost. But still, we can have very large current. So this means that we can create basically huge, where is the, yeah, here. I don't see this. Yeah, okay. You can create huge magnetic fields, basically. So therefore, this gives rise to huge applications, right? So superconductivity has a huge promise in terms of applications. So we can create magnetic levitation, we can create trains. There are prototypes already in Japan, if I'm not mistaken, that have levitating trains, okay, which are based on superconducting technologies, okay. If you've been in the hospital and you've been in one of these machines for a nuclear magnetic resonance imaging, you've been inside a superconductor, because in order to detect these changes in the spin moments, you need huge magnets, and to create those, you use superconductors actually. Also, they are used right now in big facilities, infrastructures like that they need a huge magnetic moment, like the CERN, etc., etc. Obviously, if we have cables with superconductors, we could conduct electricity without any loss, right? So this is already, I think we lose around 8% of the electricity we generate in the power centrals in transport. So with this, if we could do this transportation just with superconducting cables, that would be a huge gain. Also, the future of electrical engines and power generators, etc., with superconducting cables, it would be much more efficient. So we could do electrical engines whose efficiency is orders of magnitude the one that we have now if we were doing those with superconductors. And quantum technologies like qubits, like in the last figure, okay, are most of those that are actually built at the moment are based on superconducting technologies and properties, right? The story is that these applications are somehow still limited, and if we had a superconductor that is working in ambient conditions, obviously we would have probably a technological revolution, okay? So this is still one of the biggest challenges in science in general. So what is the state of the art? So this is a figure that shows a bit the history of superconductivity, right? Since it was discovered in, yeah, here's the mouse. Okay, in 1911 in Leiden by Kamerlingh Ons, the critical temperature was 4 Kelvin, right? So there was a lot of time, right, where this was increasing very, very slowly, right? Very, very slowly. These are the simple metals. Superconductivity was found in metals, and it was thought that it was a property ascribed to metals, right? Actually, there is I didn't put the slide here, but Matthias, which was a very good experimentalist in the 50s, who he described like 5-6 rules to discover new superconductors. He was very successful. He discovered many new superconductors. But he was wrong in many of them. So he said, get away from oxygen. Don't use oxygen. Get away from bad metals, insulators. No, these are bad. And he said also, get away from theorists. Okay? That's what, it's true, it's true. It's written there. Anyway, he was completely wrong. Okay? Why? Because then in the 80s, it was discovered the family of the unconventional superconductors. Okay? With oxygen, okay, and also magnetism. He said, no, magnetism is bad. That's what he said as well. Okay, that was another of the rules. So the family of unconventional superconductors was discovered in the 80s. Then there was another boom in the 2000s with the pnictides, okay, the iron-based superconductors. Okay, but here it's true that even if the critical temperature was increased very fast up to above the liquid nitrogen, the temperature of liquid nitrogen, which is very good for applications, this remains stacked somehow. So we have not seen any improvement there since a long time. I don't know what's the reason, but probably one of the reasons is that we don't know, or still we don't understand very well what is the mechanism behind superconductivity in these cases. And one of the implications of that is that we cannot do predictions. So we cannot do ab initio calculations, okay, of what, given a material, which is unconventional superconductor, we cannot predict what is the critical temperature of this material. We cannot do that, okay? Instead, what we can predict with current ab initio methods is the critical temperature of a material in which the superconductivity is based on the electron-phonon interaction, okay? This is something that we can calculate, okay? We know the theory. The theory was developed in the 50s and the 60s with the BCS theory of Barton, Cooper, and Schrieffer, and then Eliashberg and Migdal, or many people that work on the theory. And then in the last 20 years, we have, with big computers that we have, the ab initio methods are able to calculate the ingredients needed to enter in these equations and solve them, right? So we can do predictions. Given a material, we can calculate the critical temperature of that one if it is based on the electron-phonon coupling. So this created, and actually it was capable of predicting new compounds that were going to be high-temperature superconductors, okay? And these are the family of the hydrides that you see here in the top corner, okay? It's true that the basic idea is very simple. It's based by the Ashcroft idea, okay? Ashcroft in 1968, he said that given if hydrogen is metallic at a given pressure, okay? Hydrogen forms molecules, right? H2 molecules, but at a given very high pressure, it's believed that this is going to become an alkali metal. Okay, he was saying this metal is going to have such a high Debye temperature, so the phonon frequencies are going to be so high that basically the prefactor in this BCS theory is the Debye temperature, the phonon frequency. It can be a high temperature superconductor. So the idea is as simple as that. Okay, this is not completely correct. We can discuss about that if you want, but at least the idea it was very simple. And following this and the new ab initio methods, people were able to predict materials that were going to be high-TC superconductors, okay? And the example is H3S, okay? Where is the mouse here? H3S, okay? This material was predicted in 2014 by a Chinese group using what is called crystal structure prediction. So it's a technique that we are using it a lot. It's basically you give the stoichiometry to the computer, and the computer tries to find the crystal structure, okay? That minimizes the enthalpy. Okay, so it tries to find using like genetic algorithms, and use just completely random search, putting atoms randomly, and then going to the minima of the Born-Oppenheimer energy surface. And in this way, they construct the predictions, and they say at this given pressure, these are the crystal structures that give you lowest enthalpy. Okay, so that's what they did, and they found for this particular stoichiometry, H3S, they found a material. Then later they calculated the critical temperature using these techniques that I described, and they got something like 200 Kelvin. 1 year later, the group of Michael Eremets in Mainz, in Germany, they discovered superconductivity at a similar temperature in this compound. Okay, so it was the highest critical temperature ever measured. Okay, so what Matthias said, that stay away of theories, here it's not at all the case. Somehow I have to say that here theorists anticipated the discoveries that came out later experimentally. Okay, and it was the same later for yttrium H6, yttrium H9, lanthanum H10 as well. These materials, which were found later experimentally, okay, by different groups as well. So these experiments that I put there have been reproduced by different groups independently with different samples. Okay, I want to state that clearly because there is lots of controversy about in the field.
Is the only compound in which the only hydride, or you have only put the ones with the highest?
There are more. I have another slide later. Yeah, there are more. Yes, so basically they've been reproduced. These are solid experiments anticipated by theory, okay? Yeah, the story now came this year. So this is the state of the art in 1 year ago, let's say, okay? Then we got this complete, okay, yeah, but I forgot to say, these are very high pressures, okay? These hydrides were discovered at 100 GPa, okay? This is a huge pressure, okay? 100 GPa is 1 million times the ambient pressure, okay? It's pretty much half of the pressure we have in the core of the Earth, okay? It's something that you can reach in the lab with diamond Ambient cells, with tiny samples, and actually people are capable of doing synthesis in these conditions, okay? There are a few labs that can do that, but these are very huge extreme conditions, right? So, okay. But now this paper came in March last year saying that a hydride based on lutetium with some nitrogen, without a clear stoichiometry, with a clear crystal structure, was superconductor at basically ambient temperature, 300 Kelvin or 290 or 80, I don't remember exactly, at 1 GPa. Okay, this is nothing. 1 GPa is nothing. So you don't need that diamond Ambient cell to create this pressure. So this is much more accessible. Okay, so if this is true, that would be a complete revolution, right? Then LK99 came. This was in July. Okay, so 400 Kelvin. I was lazy enough. I didn't do the figure to change it and change the scale, so I put it up there. A huge hype in the social media, Twitter, everything. Everybody got crazy. Lots of work done. And also now there is also this other graphite that some people are claiming. There was a paper published that, as I'm going to show you now, in last day of 2023, claiming also room temperature superconductivity in this compound. So what happened in 2023? What's going on in superconductivity? Is such a big thing that it's now the moment, or I don't know, or many interests are colliding at the moment? Well, we'll see. So I'm going to tell you in the order of a bit the story, because of these materials. I'm going to just one slide on this other graphite, a few more on LK99, some more on the lutetium hydride compound, because we have worked on that, okay? In that one we have worked. I'm going to tell you what we did. So this is the paper that was published, you see, in the last day of last year in graphite. They claim global room temperature superconductivity. So basically what they are claiming is that they see zero resistance, basically, or that, when you have basically a superconductor, what you see is, I mean, if you want to have finite intensity, you need to have, let's say, zero voltage and zero resistance. 0 divided by 0, it could be any number, right? So that could be an intensity. So you need to have, let's say, when you come to, if you have a voltage and an intensity plot, when you have a superconductor, it has to be, back, here. So basically you need to have like zero voltage, right? So that's what they claim, that they see here, they see zero voltage below a given intensity, okay? So they claim it's superconductor. But anyway, if you look at the figures, these are very weird, right? So because you have, here you have basically the resistance is the slope of this curve. So here you also have some resistance. You have a slope here for all other temperatures. So it's very weird. So there's not been a hype about that, and there are claims of superconductivity in graphite. But I think this will pass. Nobody will say anything about that. Nobody believes that. But this is not what happened with the LK99. So this is 25 of July of 2023. Okay, this is my WhatsApp, okay? A friend of mine, he's a physicist, he did a PhD, but after his PhD, he quitted the academia and he's working in the industry doing artificial intelligence for a big company, okay? So I wake up and I have this WhatsApp saying, hey, okay, this is in Basque, sorry, you'll learn some Basque today. Good night, look, this paper, the first room temperature ambient pressure superconductor. This is the paper that announced the RK99. What's your opinion about that? He said, I read that the experiment is too simple to explain that, but that they are serious, he tells me. Okay, then I'm not going to read that. Then I reply, so I haven't seen it. I'm in a conference in Edinburgh, and I don't have time to go through the archive today. So it sounds a bit weird to me, but okay, I will read it and I will let you know, okay? 2 days later, another friend, mathematician with a PhD, but it's not working at all in academia, also working in artificial intelligence. He sent me again the same paper. John, have you seen that? I found it in Twitter. Yes, I said, I've seen it. And he tells me, is this new or this has something to do with the Rochester lutetium hydride thing? And I tell him, I said, I don't think it's very serious, that claim, but everybody's talking about it. And I tell him, no, it has nothing to do with the Rochester thing. And he didn't. So this is also another scandal. Your community looks like Salvame, he tells me. So, and it's a bit like that. So it would be completely crazy. So the New York Times writing a report, Kenneth Chang is one of the most senior journalists working for the New York Times on science, reporting about science, writing a report about that. Here in 5 días, furor pulsátil por el LK99. This is 2nd of August. Le Figaro also writing about that. So what's going on? The Holy Grail. So it went completely crazy out of our hands, right? So even here, Lenny was commenting here for saying this is like, I think it's 2 days later the discovery. So reporters were asking here, experts on superconductivity, okay, what's your opinion on that? No? So she was saying, los resultados no son suficientemente convincentes de que el estado observado. So she was a bit skeptical, right? Like everybody, right? Okay, good. What was the data that this paper put? Okay, so they saw like in the magnetic susceptibility, like a drop, like signatures of kind of diamagnetism, somehow of the Meissner effect. Somehow, you see here, no? Where is this? Where is the mouse? Here, right? When they were cooling with without magnetic field and when they were cooling with magnetic field, so they saw that somehow there was a drop when they were cooling without magnetic field. And then it coincided, so this transition, right, around 100 centigrades, it's very funny. I never plot these figures in centigrades. So we all use the scale of Kelvin, but here it's centigrade. And it coincided, this transition, with a drop in the resistivity. So you see that the resistivity they were measuring, it was dropping basically at a similar temperature. Okay, so that's why they thought, wow, we found that. It's fantastic. But still, if you look at the data, so, I mean, here the resistivity is huge. I mean, this is much bigger than the resistivity of copper. Here, I mean, much, much bigger. But still, they will say, okay, you can have maybe the impurities in the sample. So maybe, so if your sample is not pure enough, or there is not a connection through the electrodes that's going through a superconductor, you will have a residual resistivity. Okay, whatever. So, but the story was kind of, I think that with this hype, very serious people, very serious groups started working on that in weeks, trying to reproduce and so on. And I think it was induced by the hype in social media and in newspapers. So it's a way of doing science that I have never known before. Okay, it's something that happened this year. So, but just already in 16th of August, it's less than 3 weeks since or 3 weeks since the announcement. Okay, so this is Dan Daristo, it's a reporter that wrote for Nature, and he was saying, okay, this is already clarified. Okay, so somehow here saying, okay, this is the magnetic signature is probably ferromagnetism. That's what people were saying. And then it seems that the copper sulfide impurities that this thing had, apparently there is a transition precisely at that temperature, okay, that drops a lot the resistivity of this material. So we kind of like the pieces merge together, and apparently this material is an insulator as well, okay? So therefore, it seems that the debate was over, okay? So I was contacted by the group of Tomeu Montserrat in Cambridge. I don't know if you know him. So he's an ab initio guy doing also models, and he contacted me because apparently the crystal structure of this LK99, okay, it's a lead dope apatite, is unstable in the standard calculation. So somehow it's, if you calculate what I mean by unstable dynamically is that it is not in a minimum of the Born-Oppenheimer energy surface. Okay? So in principle, when we have a crystal structure, it has to be a structure that is in the minimum of the energy. Okay? So if you do it in classical terms, you forget about the contribution of the ions to the energy. Okay? If you forget about that, the structure has to be in the minimum of the Born-Oppenheimer energy surface. If not, there has to be another energy, which can be the fluctuations of the ions that have some given energy that can stabilize a given structure. I have some slides about this later, if I have time. I'm speaking too slow. Okay. So he contacted me and he said, okay, John, you are expert on this kind of unharmonicity, fluctuations that stabilize structures. Can you do that? And apparently, so the structures that are claimed for that material, which are these, okay, are unstable in the harmonic approximation, this classical approximation, but the structure are stabilized by unharmonicity, okay? So we collaborated on that. And also here, the band structures, as you can see, so basically when they were doing with assuming that with ferromagnetism and spin with coupling, somehow, so the system was an insulator, okay, it has a band, and it's a ferromagnetic in the calculations that Tomeu and they did in the group. So kind of like also the theoretical approach, the ab initio approach, is also consistent with the interpretation that this is kind of ferromagnetism plus, and it's an insulator, okay. So this is a bit the story here. I have this as our small contribution to that field, but I got much more involved in this one, okay. The one that happened, the Rochester one, okay. So this is Ranga Diaz, who they published this paper. So they were claiming that evidence of near ambient superconductivity in N-doped lutetium hydride. Okay. The New York Times against reported it. It was not such a hype in social media. I don't know why, because to me it was like this is well, I was working in hydrides. I am working on hydrides, right? So this comes from the group of these Ranga Diaz, who is, I don't know whether it still is, an assistant professor in Rochester University in New York, who before he had also another very controversial paper claiming that he found superconductivity in a carbon-sulfur-hydrogen compound at also room temperature, but very high pressure. It was 300 GPa or 250 GPa. So that was not so unexpected. So we had already 250 Kelvin superconductors at high pressure, 250 to 180. It was not so unexpected. But that paper had been retracted because there were some weird, some problems on the subtraction of the data in the magnetic measurements. Apparently the data that was claimed to be the measured data was not the measured data, but it was with a somehow in-house way of subtracting the noise. There were controversies about that. So, but still he had, by the Time magazine, he had been selected as one of the big important, so he had a very strong recognition in the community, I would say. So these are the evidences, okay? So it's very surprising. So they were measuring several things. Okay, where is the color change here? Okay. So basically, they started measuring superconductivity with a critical temperature of 100 Kelvin around, this is not gigapascal, this is kilobars, so it's 10 times less, okay? So 10 kilobars, 1 GPa, okay? So this is nothing, this is 1 GPa. And the critical temperature was increasing a lot, in a very narrow pressure range. So this is very anomalous with respect to the H3S, lanthanum H10, and the others. The others have, in 100 GPa, pretty much a constant critical temperature, with a very small oscillation. This is very different in that sense. They were saying that the sample had a very weird color change. So it was going from blue to red, okay? And also, and then they also measured the Raman, and there were some, let's say there were some phonons around 250 centimeters minus 1, some others below, and some very high energy phonons around 1,200, things like that. So this was the evidence they had, okay? So they presented like lots of data. So they presented resistance measurement, okay? So you see the drop of the resistance. They claim to be in, yeah, there is some controversy about that, but I mean, I read the paper very carefully. And in some of their plots here, in those, for example, they say that there is no background subtraction, so that the resistance was really 0. That's what they said, okay? Not in some other plots in the paper. In some others, they were saying, here we subtracted some noise, okay? But in those, some not, okay? Here also, this is the Meissner effect. So again, the magnetizations, you see how it drops with the zero field cooling, and with field cooling, it's suppressed, the suppression of the magnetism. And also, they presented something which is never have been presented in these hydrides, high pressure, is the specific heat measurement. So there was a novelty as well. So it looked like they had huge amount of evidence, right? So the color change has been reproduced, okay, by others. So this is another paper that came out in Nature very soon after. So it goes from blue to red, but it's true that the pressure scale is a bit different. So here they need a bit more pressure to change the color from blue to red. Okay, I didn't mention, but also they presented X-ray in the Diaz paper, okay? And they claim that the structure was FCC-like, okay? So here also they reproduced that X-ray, so it was FCC, so but basically you just see the lutetium, okay? Because with X-ray the lutetium is huge, you don't see the hydrogen, so you can know only with X-ray where the lutetium are, okay? So the lutetium, it seems to be in an FCC. If you have lutetium metal, it's FCC, so somehow not a big novelty, okay? So the Raman is also consistent in this paper with the other one by Diaz. So you have peaks at high energy, 1,200 centimeters minus 1, and then some peaks at 250 and some below, okay? But the resistance, no trace of superconductivity in this experiment, okay, has not been reproduced. But there is this claim, this is a bit mysterious, is that the paper of Russ Hemley in Chicago, Russ Hemley is a very well-reputed scientist, high pressure community, that he apparently got Diaz's sample, they take it to Chicago from Rochester, and repeat the resistivity measurements, and they claim here there is no background subtraction again, and you see that it's 0. I don't know. So it's the same sample, okay? But they repeat the resistivity. Okay, so we said, seeing at that, we said, I mean, we're working on hydrides, this is something big, we need to start working on that. So what do we have done here? So first of all, we did crystal structure predictions on lutetium hydrides without nitrogen. So we wanted to see which kind of structures we can have, okay? So this is what I told you before, we calculated the energies, the enthalpies of these structures, and we saw what we expected. So basically, that in the FCC structure, because we know from the X-ray that lutetium is in an FCC arrangement, we know that. So we have basically two candidates, which are with FCC, which are, where is this? Where is the mouse? I get lost with this. Okay, basically the lutetium H2, Fm-3m, this is FCC, and this is in the convex hull. So basically, if you mix lutetium and hydrogen, you can create chemically, you have its energetically favored to form this compound on an FCC. And then you have then Fm-3 and lutetium H3 up there. This is also FCC, okay? But it's not in the convex hull, okay? So it's not energetically favored. So there are other lutetium H3 compounds that, with a more distorted symmetry, that have lower enthalpy, okay? Anyway, as it was FCC in the experiment, we considered that maybe the parent structure were or this one, lutetium H2, or this lutetium H3. So we analyzed them further. So these are the crystal structure. You see the in lutetium H2, okay, here it is. you have the FCC lattice, and the hydrogens go into the tetrahedral interstitial sites. Okay? In lutetium H3, the hydrogens go to the tetrahedral interstitial sites and the octahedral sites. So you fill all the interstitial sites, that's all. Okay? So these are the phonons, okay? So somehow here of this one, so you have phonons very energetic, around 1000 centimeters minus 1. So this is somehow consistent with the high energy peak that it's observed experimentally, but not with the peak that you have here at 250. All these modes, these acoustic modes, phonon modes, are coming from lutetium. This lutetium H3, it's very interesting because it's stabilized by these quantum and harmonic effects that I was referring before. And you have phonons that, okay, where I get very lost with this one. Okay, here. That, okay, maybe they can explain also the 250 peak, maybe. I don't know. It's a bit maybe optimistic. Then we calculated the reflectivity, okay? And it's very interesting. This lutetium H2, this one, explains the color change, the blue to red change. And it's very interesting. So this is as a function of pressure, the reflectivity. So you see that in the far infrared, this is highly reflective. So these are ab initio calculations, okay? I'm not going to enter in the details now. You can ask. So you see that it's highly reflective, but then later in the visible, there is a plasmon, okay, that sucks all the light, so it's not reflective anymore, okay? What happens is that when you are at low pressures, so let's say the plasmon, it's very in the edge of the visible range, but this starts shifting to higher energies, okay? And therefore, when you are at higher pressures, you leave this kind of reflective visible in the red, okay? So that's why you explain the color change. So actually, the color of the line is the color that we should see from this reflectance spectra. So you see that it goes from blue to red as a function of pressure, right? On the contrary, this one, I mean, it's gray. So this one has nothing interesting in the color, lutetium H3, nothing. So this is the reason. You see, this is the plasma that I was referring to, okay? It appears because there are very intense interband transitions in the bands around 2 electron volts. So therefore, this gives rise to an undamped plasmon. So this is the real part, the imaginary part of the electric function. So it has a strong peak here, which is related to these transitions. And therefore, by Kramers-Kronig, this makes pass the real part from here when the imaginary part is 0. So there is an undamped plasmon here in the loss function. And that's why it's very sharp, and this explains the color change in this material, okay? So somehow in conclusion that to us, what was the conclusion? It's that lutetium H2 seems to be the parent structure here because it explains the color change observed there, okay? But maybe you need some hydrogens in the octahedral sites to explain the Raman, this other peak in 250 centimeters minus 1. We obviously calculated superconductivity in these materials. Lutetium H2, 0, no superconductivity. The one that explains the color, no, there is no superconductivity there. And the other one, lutetium H3, yeah, 20 Kelvin at 6 GPa. Nothing compared to ambient pressure, right? So we said, okay, maybe there is something that we are missing. These are not the structure. So we did crystal structure predictions, also including nitrogen. We did it for lutetium H2 and lutetium H3. No. I mean, if you draw a line, you expect something in between, but it's maybe not the truth, obviously, no. So then we added nitrogen and we did crystal structure prediction. So this is like the energetics, okay, a big mess, but many crystal structure prediction, many compounds that we analyzed, and there is something that we did here, okay. Oh, this is not the figure that I expected. Okay, something happened here when transferring the data. Never mind. So we have a way to predict the critical temperature based on something that we call the networking value. It's based on chemistry. Doesn't matter, but it gives us somehow like the critical temperature with an error of 60 Kelvin. it's huge error, right? But if you want to predict a superconductor of 300 Kelvin, it's enough. Okay? So we somehow, in all these crystal structure predictions for lutetium, hydrogen, nitrogen compounds, we calculated with this very fast estimator the critical temperature. Okay, the maximum we got 13 Kelvin. Nothing. So basically, here we believe there is no superconductivity in all the structures, stable, metastable, in a range that where we consider reasonable for metastability. Nothing. And this is consistent with other people. Many people have done crystal structure predictions, also including nitrogen, so nobody finds anything that can be a high-density superconductor. We gave them another possibility, another option, okay? And we consider this kind of templates, okay? This template, because this is the one, lutetium H10, this is the one that gives in lanthanum the high TC of 250 Kelvin, okay? This is very far energetically. So it's like pretty much 1 electron per atom above the lowest energy structure. So it's impossible that this is synthesized experimentally. Also, the X-ray similarity is very low. So it's very different from X-ray. Okay, so no, cannot be. We took this one because this is also another template that in other hydrides has been shown to give high TC superconductor experimentally. Also, this is very far energetically from the convex hull. This is a huge energy. And also, it's very different from X-ray. Okay? Then we took this one, which is the lutetium H3, but we substitute out of 4 hydrogens in the octahedral side by 1 nitrogen. So this is nitrogen. And this is a bit closer to the convex hull, but it's still very far, okay, energetically. But maybe one could say, is this metastable? Yes, no, I don't know. Here, this by X-ray, this could be confused with the X-ray, because basically it's FCC and the volume is basically the same, okay? So it's interesting that all of these structures are stabilized by quantum anharmonic effects, okay? I'm going to talk about that later. And here at 20 GPa, okay, these are dynamically unstable below these very high pressures. So, I mean, these will never be able to be synthesized at low pressures. But this one, I don't know. So here we believe that above 20 GPa, this is dynamically stable. So we can have an error in the calculations, okay? 20 GPa is not that much, okay, in terms of, in this scale. So maybe this is dynamically stable also at lower pressures. And the TC that we calculated is 100 Kelvin, so it's not that bad here, okay? So I was a bit curious about this. So maybe there is here something. And the interesting thing is that if we compare, this is very similar to lutetium H3, okay? And which has a TC of much lower. So here we are substituting out of 4 hydrogens in the octahedral side, 1 nitrogen. And we get a TC increase of a factor of 3. So still, this is very low from the experiment, right? It's much, much lower critical temperature. It's not dynamically stable in our calculations at ambient pressure. It's not thermodynamically stable. But there is something. So here, basically, what I'm saying is that when we are adding this nitrogen, something is happening that is increasing the critical temperature here. That's for sure in this compound, even if this is not thermodynamically stable. And the reason is in the electronic properties. So you can see the density of state at the Fermi level is increasing a lot. It's basically doubling when we include the nitrogen. So chemically the things are changing. And somehow, to me, this is saying, I don't know, I don't think we are explaining at all the experiment here, no. But I'm saying here that maybe there are some hydrides that actually, with doping and engineering things, can give high TC values at low pressures that are high, okay? So basically, this is it, okay? Okay, this doesn't appear very well, okay. Anyway, the paper got rejected, okay? Got rejected, and why it got rejected? It got rejected because from, I think there were 11 authors in that paper, 8 of them asked to retract the paper to the editor in Nature, okay? Here, it was a screenshot, I don't know, in my computer it looked okay, here no. This Dan Garisto, this journalist that wrote for Nature the other comment, on Twitter, he leaked the letter that DSS sent to the authors, okay? asking them not to ask this, the retraction of the paper, okay? And you can see, you can go, I put it here, you don't read very well. So I underlined some things there that, that they were, you could see what they were writing in the letter to the editor, okay? And they were saying, okay, that there was some kind of manipulation of data, not treatment, not saying exactly the truth, scientific truth, in the method section. So there was something obscure here, okay? But let's forget about it then. So let's forget about lutetium hydrogen nitride. Again, yeah, all these things that, all these things that have gone away, no, and I think it's a good moment at this moment with what has happened to ask ourselves how we do science, how the peer review system. I think all these things ask lots of questions, right? So the role of the journals and so on. I'm not going to enter there, okay? But there is hope. Everything is smoke here, or there is hope. So I'm going to say that yes, there is I'm going to be optimistic. Okay. So this is another plot of the, let's say, the state-of-the-art superconductivity. Here I put pressure and the critical temperature of many compounds, and I put them I include some cuprates, the best cuprates, and magnesium dibride as well in this plot. Okay. So obviously we want something here. Where is here? Right. This is what we want. The thing is that in calculations we are starting to get new predictions which are very interesting. Okay. This is a prediction we collaborated. Okay. This one. But one day later in the archive. So when we put the paper in the archive, Chris Pickard wrote to me saying, "Hey John, we have the same result, completely independently." And they put the paper in the archive one day later or 2 days later, okay? So basically this is this compound. Here we have a problem with it. So it's magnesium iridium H6, okay? So this is we had a small contribution here, so all the credit goes to Miguel Marquez's group in Germany, okay? So basically he has a machine learning kind of algorithm to calculate convex holes of materials of stability. So basically he uses machine learning predictions. He has a huge database of materials, a huge database, and from that database of materials he can generate the convex holes of different type of stoichiometries very fast using machine learning potentials, etc. So he has a very sophisticated machinery to do these kind of predictions. So he was doing basically these predictions, and he came out with this compound, magnesium 2 iridium H6. According to his calculations, this is thermodynamically stable at ambient pressures. And the critical temperature that was calculated is 80 Kelvin at ambient pressure. 1 day later, the paper by Chris Pickard and so on, they also have another different, very sophisticated method to do crystal structure predictions and so on. It's different, so it's not machine learning based. It's based on machine learning potentials, but not on a machine learning prediction by itself. And also they got the same compound with the same crystal structure. They were saying that it is not thermodynamically stable, they were saying, because it's true they were considering other stoichiometries that here, Miguel Marquez and so on, they were not considering, but they were saying that at 20 GPa, yes, and therefore it could be kind of quenched to ambient pressure. So they were also very optimistic about that. And the critical temperature they were predicting was higher than us for the same compound. So they're saying, okay, maybe the theories also, when we are doing the same type of calculations, maybe we have disagreements, because to me this disagreement is a bit high, okay? So, but this is very interesting. So it seems that there are compounds that can be predicted to be thermodynamically stable or close to be thermodynamically stable, at least here at ambient pressure, that have a high TC similar to the cuprates at least. So I think this is going to happen. Okay. So I think I'm running out of time, right? So basically this is a bit the flow chart of Miguel Marquez's work, in which we collaborated a bit. Okay. So basically he has a huge database of compounds of 4 million entries. Okay. So he chooses some of those basically based on thermodynamical stability, which are closest to be close to thermodynamical stability, and then how he trains the machine learning machine for a given compound. He trains using harmonic phonon calculations and electron phonon ab initio calculations. So basically, and this is he trains that way. And therefore, when he trains the machine with ab initio calculations of, let's say, 7,000 entries, okay, he can go to all his database and predict the critical temperature of these materials with this machine learning algorithm. Okay? The story is, if there is a structure that is unstable in the harmonic approximation, it's neglected by this flowchart. Okay? So what I'm saying basically here is that there is a huge room for predictions based on these techniques. But, and this is the message, it's not at all exhausted. Okay? Why? Because as I said, it is neglecting all the structures that are unstable in the harmonic approximation. And we know this has been my work, and I basically didn't speak much about my work in this talk, and I think I have no time. I have some more slides here. But basically what I'm saying is, maybe let me just go advance a bit. Yeah, a previous one. Okay. I just want to say that these quantum and harmonic effects, I don't know if you understand what I mean by that. Can we take some 5 more minutes? Okay, so then I will explain a bit. Yeah, this is what I mean. Okay. Let me just explain that, okay, a bit. So that I mentioned that throughout the lecture, but maybe I was not specific enough, okay? So imagine we have this is the Born-Oppenheimer potential of a given compound. We have energy and we have R. Let's say it's a collective variable that determines all the positions of the ions. So what is the classical harmonic picture? So we would go to the minimum of the potential, right, here, right? And we would place the ions here, okay? But this is not the total energy of the ions, the total energy of the system. What do we miss? Because the Born-Oppenheimer energy, remember, is the electronic energy for a given positions of the ions. That's this energy. Then we will need to add the 0-point motion energy of the ions, right? Because at 0 Kelvin also the ions fluctuate with the 0-point energy. 1/2 h bar of omega, right? So an omega is coming from the second derivative of the curvature here, right? Let's say we calculate that, the total energy, we add that to this energy, so this is the energy we get, right? Imagine we solve the here with, this is a 1D potential. We can solve exactly the Hamiltonian with this Born-Oppenheimer potential. The energy we get is this one, okay, much lower. And I put the point here, why? Because if we calculate with that wave function that we calculate numerically, if I calculate the expectation of the position operator, let's say, which is the most probable position where I can find the ions, in this case, I get it in this position, here, very far from the minimum of the potential, right? Why is this different? Because the 0-point energy, it's much smaller for this case. So when we add the total energy plus the 0-point energy, in this case, is smaller than when we have here this, right? So this is what I mean about quantum anharmonic effects, right? Why quantum anharmonic? Because anharmonic, you need the full shape of the potential to get that value. If not, if you don't have the full anharmonic potential, you don't have that value. And everything that I have done in the last basically 10 years is to develop an ab initio method to get these kind of things correct with the full interacting anharmonic theory, and that's why we've been kind of relevant here. So we developed the SSCHA method. It's a method to get these calculations done for solids. And when we apply this theory, that's the energy we get. It's very close to the exact energy, and the positions of the ions is also very close to the real expectation value of where the ions are. So that's why we have a good theory here to treat with these materials, right? So let me just tell you this story. Previous. So this is, for example, lanthanum H10. Okay, so we applied these for many hydrides, H3S, lanthanum H10. We've been working for charge density wave materials, ferroelectrics. So these ideas are important for all these kind of systems. But what I mean here is that this is lanthanum H10. Lanthanum H10, which has, this is experimentally well understood, it's solid, has a critical temperature of 250 Kelvin at around 150 GPa. If you calculate the harmonic phonons, you get them completely unstable. The structure that you observe experimentally, it's not at all stable. And why is that? Why it's not stable in the harmonic approximation? Because if you calculate the harmonic phonons, okay, they have a contribution coming from the electron-ion interaction of our electron-ion interaction. What is this contribution? It's like a Linhart function, okay, weighted by the electron-phonon matrix elements. Basically, this is analytic. This is the harmonic contribution of the electron-ion interaction term into the harmonic phonons, okay? So this means that if you have a strong electron-phonon interaction, okay, and this is negative definite by construction, the contribution of that. So it's negative definite. So if this is big, the phonons will be suppressed, right? Go down, okay? So the reason why we have huge harmonic instabilities here is because the electron-phonon interaction here is huge, okay? What happens here? These quantum anharmonic effects that I was talking about do stabilize this structure. So actually you see the anharmonic phonons are the red ones. There's no imaginary phonons, okay? So somehow they are stable thanks to these quantum anharmonic effects. So the message is here. Quantum anharmonic effects can stabilize crystal structures with a huge electron-phonon coupling that otherwise are unstable, right? So that's why I think we need to have hope. So instead of training this kind of machine learning with harmonic phonons and harmonic electron-phonon calculations and discarding all the materials that are unstable, right? I think we can have new predictions that probably are interesting. And I think that we can hope to find something, right, in at least this area. I think that this is realistic. So I think there is work to do in the field. And I think that in the next 5-10 years, I think we'll have good results in this area. So I think that there is, I want to be finished saying that I am optimistic about the future. So I think there is not just smoke in the air. So thank you very much for your attention.
Thank you so much for the talk. Very interesting. So, are there any questions?
Hi. Thanks for the nice talk. Is there a way in which you can have some intuition on which materials are going to could work or not among all these, like both in terms of combining the stability and the and the thesis.
That's the key question, right? Yeah, because actually the periodic table is so big, right? Some people will tell you yes. So, for example, that there are some ideas. For example, if you go back to this crystal structure, this is the lanthanum H10. Or where is it? Did I put the? Yeah, this is the crystal structure of lanthanum H10, for example. Okay, so. There is a very interesting paper that says that where do the hydrogens go here? And it seems that they go to places in which there is a strong electron localization. So if you remove the hydrogens here and you just do a DFT calculation of the electronic density of the lanthanum, let's say, scaffold, okay, you see a strong electron localization where the hydrogens later are absorbed. So this maybe is the chemistry that is behind the formation of these high electron phonon coupling materials, okay? So what we know is that what you need is that this kind of hydrogen-like network is covalently bonded between each other somehow. This is what you need biochemically to have a large electron phonon coupling here. This is, in most of the cases, this is what you see. And actually this is the basis that we use to predict the critical temperature very fast with this big error, but we use it and it's useful. So I think this is the maybe, so therefore this is a bit where the chemical intuition goes. So we need to find materials that have a strong, could be like, what's the name, like, what's the name of these materials that have like a strong electronic strong electronic localization in interstitial sites. They are called like they call them like fake atoms in these sites. Okay, never mind. So these kind of materials maybe could be a potential for really absorbing. But some others tell you forget about that. What best works here is brute force. So let's say like this machine learning thing is completely brute force. So you have a huge database of materials, and let's try to do it. The thing is that I think that these kind of searches are not exhausted, of course, because of the reasons that I gave. So some people tell you that, okay, maybe there is some chemical intuition that can guide the search, but some others tell you, okay, let's forget about the chemical intuition, let's do it brute force, because it's the way to find things that, if not, would surprise us. Because I remember talking in when H3S was discovered, the chemists went crazy. Sulfur to, you can only absorb 2 hydrogens, not 3. It's impossible, they were going crazy. It's like, no. So it's chemistry that we don't know. So somehow the chemical intuition is not useful to this, it was not useful to discover H3S. Of course, at 150 GPa, the chemistry is completely different. So how are we, maybe the surprises are there. Maybe brute force is more effective to find the new surprises. But I think that I agree with you that maybe there is some kind of chemical intuition, and I think it's going along the lines that I told you, that can give us some hints or some, let's say, search strategies as well. Yeah, that's a very good question. I didn't want to enter into, I wanted to make more didactical talk, but so it's a variational method. So our approximation is that we kind of have, our approximation is that our ionic wave function is Gaussian, like in the harmonic calculation, okay? So if you want, so we have a Gaussian, we try to find the Gaussian wave function for the ions, that minimizes the total energy. So therefore, we do not approximate the potential is exact, okay? But we, instead of doing this variational minimization, we do not make any, what we do is we do a Monte Carlo-like sampling. So therefore, we don't calculate explicitly all the Taylor expansion of the Born-Oppenheimer potential. No, we don't do it, and we avoid that because this is impossible, basically. So we avoid that by a Monte Carlo sampling somehow. So in the end, what we do is we create some set of configurations for the ions distorted according to a given Gaussian distribution function. We need to calculate the forces for these distribution functions, for these ionic configurations, and with those we can perform the variational minimization. Okay, this is the idea somehow behind the SHA method. Yeah, so the software is free. We have some lectures that we did in June, so there are some videos. If you, sha.eu is the website. So, I mean, if you are interested, you can see we have videos. Hopefully they are clear enough, and the school was clear enough that we did in June, last June. Yeah.
So when you discover that some material is thermodynamically stable according to your simulations, how difficult is to convince experimental groups to try this, or how far or close they are to actually test these predictions in terms of synthesis of materials?
Yeah, that's, the experiments here are very challenging, are very, very difficult. So, but given, I think that they are starting to trust us, right? Because it's true that la batería. Okay. Now do you hear me? Now do you
Sí,
hear
sí.
me?
El 3.
Now?
¿Hola? Sí,
Hola.
¿habla?
No se oye, ¿no?
Qué raro.
Vale, sí. So I think they are starting to trust us because we've been kind of successful, right? So the thing is that, so somehow the binaries hydrides are exhausted. So let's say all the hydrogen with pretty much all the other compounds in the periodic table, theoretically they have been studied. And I would not expect more surprises there. Then the story is ternary compounds, right? Yeah, the chemistry of let's say the convex hull, where I was plotting which is thermodynamically stable with 2 compounds, with 2 elements, is simpler. When you have 3, instead of having a line, you have a triangle. I mean, I was showing a triangle. With 4, I don't know what you have, so something more. We need 3D already. So the chemistry becomes much, much, much more complicated. So it's true that with the binaries, the predictions have been kind of successful, not always, because there are some systems that were predicted theoretically and were guiding experiments, and experimentalists tried, and they were not successful in the synthesis of these compounds. This is true. There are many different reasons. 1, because maybe the synthesis is very complicated. 2, the calculations have obviously approximations that are not really giving you which is the best thing. So I don't know exactly which is the reason, but in each particular case, there will probably be a reason. I think that what is kind of clear by the experimentalists, they assume that we can give good suggestions, so and they can try. So, but it's true that it's not given that all these predictions will be later realized experimentally. So it's not easy to convince them, but I think that the facts that all these hydrides were predicted before, it's given them some ideas later to try. So there is this, this one here, for example. This one, so the orange are experimentally synthesized, okay? So, for example, this template as well is a template. This one, and this one are similar. So the green are predictions, and the orange are experiments. So also this template was also predicted. It's a ternary already that was already predicted before by experiments. So they were trying. So I think that even in ternary compounds, it will be more difficult because the diagram is much more complicated. There are many, the synthesis paths are many more. The dissociation paths, sorry. So it's going to be more complicated. But still, for example, this one ternary that was predicted theoretically before, it was synthesized experimentally.
Are there more questions? Well, no. If not, let's thank Ion again. Thank you so much.